Today we start looking at the ideas of momentum, okay? So if you could rank the following from strongest to weakest, the impact each object would have. So let's say we have a pebble that hits us moving at 90 miles per hour, a Hummer that hits us moving at 20 miles per hour, and then a baseball that hits us moving at 30 miles per hour. Which of the following ranked from weakest to strongest? Let's go weakest to strongest in this case, so strongest to weakest, because that's a little bit weird. The impact each object would have if they were to hit us. So we can't make a for sure prediction because we don't know the masses of each object, but we can say for sure there are two factors that probably affect our judgment the most. One, the mass of the object, and two, how fast the object is moving, aka the velocity of the object. So that's what we're going to take a look at today, is what does mass and velocity have to do with the inertia and strength of motion of an object. So today we're looking at 4.5, the momentum, impulse theorem, momentum, and impulse. So some announcements, please disregard these announcements right here. I recorded this video prior to this lesson being done, so I've yet to update the announcements. So we're up to today. What are momentum and impulse? How can we mitigate / reduce the force acting on an object during a collision? And where might such scenarios be applicable in our daily lives? So momentum and impulse. Momentum, represented by the letter P, is a measure of the inertia and the strength of motion of an object. Momentum depends upon mass and velocity of an object, like we saw on our beginning slide. The units for momentum are kilograms meters per second. All right, so here's our equation for momentum. P equals mass times velocity. So the units for momentum are simply the units for mass multiplied by the units for velocity, kilograms times meters per second. An impulse, J, represented by the letter J, is defined as a change in momentum. So an impulse is going to be represented by m times delta v, mass times our change in velocity, and that represents a change in momentum for our object. So like we were talking about before, we can see the momentum of an object depends on the mass and the velocity of our object. So two very distinct but very interconnected factors. So let's take a look at an example of the momentum and impulse. Okay, an 80 kilogram linebacker is running at a velocity of 12 meters per second to the right. When realizing they missed their mark, they turn around and run at a velocity of 8 meters per second. We ask, what is the impulse of the linebacker? Okay, so using the definition for impulse, we're going to have impulse equals mass times change in velocity, which is going to be mass times our final velocity minus our initial velocity. So if our mass is 80 kilograms and our final velocity is negative 8 meters per second, negative 8 because our person starts off running to the right and then turns around, meaning they're heading to the left, then we're going to subtract the 12 meters per second. So we're going to have negative 8 meters per second minus 12 meters per second. So plugging this into a calculator is going to give us negative 1,600 kilograms meters per second. So here's a water balloon contest that we're not going to be able to do here. But we'll discuss some of the factors if we were to carry out this hypothetical water balloon contest that might affect the impact force acting on a balloon. So if you may recall, in a water balloon contest, we want to prevent the water balloon from popping, which means we got to decrease the amount of force acting on the balloon from our hands. So here are some ways that we can do this. We can move our hand with the balloon, and in doing so, we're going to increase our time of impact, because by moving our hand with the balloon, we're increasing the time of the catch. So that increases the time of the impact. What we can notice is that this subsequently decreases impact force. The other way we could do this is we could throw the balloon underhand instead of overhand. And in doing so, we're going to decrease the velocity of the balloon so that when the balloon hits our hand, it's not going to hit our hand with as fast a velocity. And then the other thing that some people noted is that we can make the balloon smaller or less full of water, which means it's less likely to pop. In which case we're decreasing the mass of the balloon. Okay? So all these factors, impact time, velocity of balloon, mass of balloon, can all be related to the impact force through what's called the momentum impulse theorem. So what the momentum impulse theorem states is that a force acting over time causes an impulse change in momentum for an object. So force times time is going to cause a change in momentum, mass times change in velocity. For a given scenario, the impulse will remain the same, so you'll have the same change in momentum, while impact force and impact time will have an inverse relationship. If time of impact increases, then the force will decrease. And if time of impact decreases, the impact force will increase. So again, we can think about this from perspective of our water balloon example. If we increase the time of our catch, we move our hands with the balloon, that decreases the force acting on the balloon. And if we decrease the time of impact, like let's say we slammed our hand into the balloon, then that's going to increase the impact force of the balloon, make it more likely to pop. So while this right-hand side will remain the same for a given scenario, force and time can have an inverse relationship. As force decreases, or excuse me, as time increases, force decreases, and as time decreases, force will increase. So the idea behind this, this theorem here, this concept, is actually the basis for the expression to roll with the punches. If you've ever heard the expression to roll with the punches, it essentially means that if you can't avoid damage being done, you should try to minimize the amount of damage that is done, that will be done. And so you can do that by rolling your face with the punches by moving your face with a punch. And the idea is for a given change of momentum, the change of momentum being the same in both these cases, if you move your face with the punch, you're increasing your time of impact and thus decreasing your impact force. Okay? Whereas if you don't roll with the punches, if you keep your face here or you move your face into the punch, you're going to decrease the time of impact and thus increase the impact force. So for a given change of momentum, there is going to be an inverse relationship between impact time and impact force. So here's a quick check for understanding then to see where we're at. Two identical cars, each moving at the same initial speed, encounter a collision. One collides with a haystack while another collides with a brick wall. In A, we ask, how does the impulse of each car compare? And then in B, we ask, how does the impact force in each car compare? So please take a moment to answer and we'll bring it back together to discuss together as a class. So let's take a look at A here. How does the impulse of each car compare? So if we take a look, impulse is going to be a change in momentum, okay? So it might be tempting to say that the change in momentum is greater for the brick wall than for the haystack. What you have to consider for change in momentum is what's happening with the mass and the change in velocity of each car. So each car has identical masses because they're identical, okay? And we know each car has the same initial speed. If both are colliding with the haystack and brick wall, both cars are going to come to a stop. So they're going from the initial speed, the same initial speed to the same final velocity, which means the change in velocity is the same. So as a result, because the mass and change in velocity is the same, that means the change in momentum is the same, so thus the impulses are the same in both cases. Now we ask, how does the impact force on each car compare? Well, with the haystack is going to move with the car, which is going to increase the time of collision, whereas the brick wall is not going to move with the car, which is going to result in a very short time of collision. So because of that inverse relationship between impact time and impact force, we know that the impact force of the haystack will be significantly less than the impact force for the brick wall. So applications of momentum impulse theorem in everyday life that we see in engineering, concussion and head safety technology, helmets are being designed to maximize impact time and thus reduce the likelihood of severe amounts of force, extreme amounts of force acting on the head, say in football or other sports. Safety features of car crashes, such as a crumple zone, which we'll see right here. So modern cars are designed with crumple zones in the front and back that are designed to crumple in on themselves, which sounds paradoxical because if you're crumpling in on themselves, it's like it's putting the people inside at risk. You know, we don't want other cars getting closer to the people inside, so why do we want a crumple zone? Well, the idea is that by adding a crumple zone, you're actually increasing the time of impact on the car and thus decreasing the impact force acting on the car, which keeps the people inside safer. Whereas if you didn't have a crumple zone, that would be a very short time of impact and thus there would be a high amount of impact force acting on the people inside the car. So let's look at some momentum impulse theorem problems here. So a 2,000 kilogram car that is moving at a speed of 21 meters per second crashes with another car, bringing both cars to rest. If the impact force needs to be negative 10,000 newtons, what must be the time of impact for a collision? So the way to identify if you need to use momentum impulse theorem for a problem is that if the problem gives you force and asks you to look for time, or vice versa, gives you time and asks you to look for force, then you're always going to use a momentum impulse theorem, okay? So in this case right here, we write down what information we know and what we're looking for. So here we know our force is negative 10,000 newtons. We know our mass is 2,000 kilograms. We know our initial velocity is 21 meters per second. And we know our final velocity is 0 meters per second. We're coming to rest, okay? And we're looking for our time of impact. So this tells us right here, because we have force and we have time, we are going to need to use a momentum impulse theorem. So force times time equals mass times change in velocity, or mass times final velocity minus initial velocity. So that's going to be negative 10,000 times t equals 2,000 times 0 minus 21, okay? Or negative 10,000 times t equals negative 4,200. So dividing both sides by negative 10,000 tells us that our time of impact is going to have to be 4.2 seconds. And thus that is a sample problem for the momentum impulse theorem. So now try this problem on your own right here. A football player's helmet can sustain a maximum force of 7,000 newtons over a span of 0.1 seconds. If the mass of a linebacker typical human head is 6 kilograms, what is the maximum velocity that the linebacker starting from rest can go without sustaining injury? So in this case right here, again, we're given force and we're given time. So we recognize that we need the momentum impulse theorem here, okay? So force and time are known to us. Force is 7,000 newtons, time is 0.01 seconds. We know mass is 6 kilograms. We know our initial velocity is 0 meters per second. We know the final velocity, the velocity that our person is speeding up to, is going to be our unknown, okay? So as a result, using momentum impulse theorem, we're going to have force times time equals mass times final velocity minus initial velocity. So now we can plug in our known information in order to solve for our unknown. So we have 7,000 newtons equals 0.01 seconds equals 6 kilograms times our final velocity minus 0. And so as a result, we're going to get 70 equals 60 equals 6 times VF, or dividing both sides by 6, our final speeds, the maximum speed our person can go, is 11.67 meters per second. So that's how fast our person can go in order for our helmet to work effectively. Anything beyond that speed and our helmet is not going to work effectively. And this is our lesson on the momentum impulse theorem.